Our next session is creating operational resilience. In this session, you will learn CMU-SEI's focus on operational cyber risk reduction through tools that align defense around the mission, train as you fight technologies to prepare the cyber mission force, and models, metrics, and data sets to improve vulnerability response.
Wow, that was it's fantastic. So we're in the arguably a very tough spot. We're right after lunch, and we're right before the break. So I'm going to encourage everybody to stand up. Go ahead, stand up. Take this chance. We've all been there. Stand up, stretch your legs, do some calisthenics, just to get the blood moving, and then at your leisure, you can go ahead and have a seat. Okay. My name is Josh Hammerstein. I'm team lead in the Cyber Workforce Development Directorate at the CERT Division, in the CERT Division, which is a part of the SEI. And with me today is Dr. April Galyardt, a machine learning research scientist, also at the CERT Division. Just in case it comes up, if anybody was wondering, that picture of me that was taken yesterday. So we'll get that out of the way before the Q&A questions start. So today we're here to talk to you about operational cyber risk reduction. And what we really mean by that is reducing risk so that the US government and the DoD can field and operate systems to support their missions even in the face of a capable adversary. As is going to be a common theme throughout the next 2 days, as we talk about this work of reducing operational risk, it's important to understand how they relate to these 4 challenges that we're going to be talking about that need to be addressed in order to make software a strategic advantage for the DoD. Trustworthiness, timeliness, capability, and what's the 4th one? Affordability. So making software more affordable, reducing the cost to operate and acquire software, providing better capability to our warfighter to support existing missions and new missions, ensuring trustworthiness in software, and being able to have assurance in its operation and construction. And then timeliness, making sure that software is acquired at a cadence that is commensurate with the operational tempo of the warfighter. What we're going to be talking about today are a few projects that relate to reducing operational cyber risk. And they fall along 3 main themes: better tools, better training, and better practices and policies. So with regards to better tools, the question we're going to be trying to answer is, how do we get inside the head of malware authors? How can we better understand the malware and software that they write? With regards to training, how can we bring the experience of an expert instructor to every single trainee in the DoD? And then finally, with regards to better policies and practices, when the next Spectre and Meltdown come, how are we going to handle that? So with that, I'm going to hand it off to Dr. Galyardt to start talking about better tools and better training.
So the problem that we're trying to address here with the better tools is malware. The job of a malware analyst and reverse engineering the software to figure out what the malware is doing and what vulnerabilities it's trying to exploit, it's tedious and it's time consuming, and you're often taking a representation of the binary and looking at it and trying to reason backwards from various representations. And so the more we can build tools to speed up their work and make it easier for them to understand that software, the better they can do their job. And so there's a couple of things that are already out there. So Pharos is a system that's out there. It's built on top of ROSE, which was put together by Lawrence Livermore Labs. And it's on GitHub. It is already an automated executable analysis platform. And there's a capability that was just added to it, and this paper is coming out next week, in terms of looking at object-oriented software and reverse engineering the object-oriented software. So when we write code in a language like C++, we're taking advantages of classes and methods so that the code is more readable, so that it's easier to design and think about what the program does, and you've got these objects that you can reason about. But when you compile it, all of that structure that makes the code easy to understand gets optimized and flattened, and it disappears. And so what this new capability that was just added does is it recovers a lot of that structure and makes the malware analyst's job that much easier. Now, the ONR project that's mentioned here, we are in year 1 of a 5-year project, and the goal of that project is if we're going to deploy software in a mission situation and it has extra features that are really unnecessary, that increases the attack surface. So if we can take out some of those unnecessary features and reduce the attack surface, then that is a very good thing. And we did say tools, so we're going to talk about quite a few different tools. This one is a tool for the malware analyst as they're doing their job. And you have, so one of the things that they very often do is when you have a piece of malware, you run it in a sandbox environment so that you can see what it does and what kind of vulnerabilities it's trying to exploit. The problem is the malware author knows you're going to do this. They know it's going to get run in a sandbox, so they put in all kinds of conditions and things so that maybe it'll only run in a Chinese environment, or maybe it will only run on a particular operating system with a particular set of systems set up. And that makes it very hard for the analyst to see what it's doing in the sandbox because they don't know what conditions to set their sandbox up with. So if we can streamline the program and take out some features and have it execute the way, the full badness of the malware, so we can see what vulnerability it's really trying to exploit, then that makes the job easier. So the Pathfinder is trying to get from the starting to the target behavior, the really bad behavior. Because one of the things they'll do is sometimes they'll execute, it'll just scan for things that look like credit card numbers. But that's not really what it's going to do when it's in the full system. So we want to get all the way to the target vertex, that's the really bad behavior. And right now there are, the team has come up with 2 approaches that solve this problem. And one of them is pretty slow, but very accurate. And one of them is fairly fast and not so accurate. So this is year 1 of a 3-year project. So over the next year, that is, let's combine these approaches and find something that is both fast and accurate, and then get to work on creating this rewriter so that at the end of the 3 years, the malware analyst has this great tool. Speaking of structure that disappears when you compile code, variable names disappear. When we write code, we use meaningful variable names, because if you've got a variable in there that's a buffer, maybe you're going to call it buffer or buff or something that makes sense. And this is really good for human memory, because working memory overload is a bad thing. But when we decompile code, all of that disappears, all of that structure. And so you're trying to remember V15, oh, that's the buffer, and A3, that's something we're going to iterate over. If we can recover some of that structure, it makes the malware analyst's job that much easier. And so right now, again, this is ongoing work, but right now there's a program that exists that will recover semantically meaningful names, and it recovers exact matches and abbreviations in 16 to 17% of cases. Now, it sounds like a really low number, but that's exact matches and abbreviations. So that's a lower bound on performance. And working on better metrics, but anecdotally, it actually seems like some of the meaningful names that have been recovered are actually more useful for the malware analyst than what was originally in the source code. So this is, again, ongoing work. So what's next? I've already mentioned the pathfinding work. The next step is to find something that is fast and accurate, and then build the full tool. But I do want to talk about 2 projects that are coming online now. The first one is in terms of investigating the accuracy and reliability of the ARM executable software tools. We have lots of existing tools for analyzing software that runs in desktop environments. But with the proliferation of cell phones and other small electronics that are running on a different architecture, we need a way to study that software and see how well that software is performing. And so this is a first step in that direction in terms of, are the existing tools for evaluating software on the smaller devices, are those tools good enough? And if where are the gaps and how do we make them better? So that project's coming online. And then the last one in this malware area is we're going to examine the efficacy of protections against code reuse attacks. So code reuse attacks, this is also return-oriented programming. The most well-known example, kind of the stereotypical example, is the return into libc, if that rings any bells for some of you. But what's going on is that your malware author is writing an attack that takes advantage of libraries already in the system and how those libraries are loaded into memory and they can execute instructions based on how that memory is handled. And so these return-oriented, the ROP gadgets, it only takes about 12 of these gadgets to find a vulnerability that you can exploit. So 12 objects. And in a typical environment, you might have 70,000 of these. One of the biggest problems with current research in this area is the metric of how we're checking whether or not those vulnerabilities have been remediated. And that is, if you just reduce the number of available objects, it seems like you're doing great. It's a 70% reduction. Well, if you've gone from 70,000 to 3,000, that sounds like a really big improvement, but it only takes 12 to find a vulnerability. So 3,000 is still a lot of attack surface. So a big piece of that work is going to be finding metrics so that we can actually measure how many vulnerabilities we're remediating and exploits we're preventing. And I want to mention again, the Pharos system it's available right now on GitHub. So as many of these tools as we can make available for general use, I consider that a good thing. So now we're ready to talk about training, completely different set. The problem that we're addressing here, there's a global shortage of cybersecurity professionals, and the DoD is not exempt, and you might argue that the DoD suffers from this shortage worse than a lot of other areas. So we need to train more people more effectively, more efficiently. And the cyber workforce development team does this. We work with the DoD to help them train as they fight. And there's on-demand training with video instruction and a big simulation, wonderful simulation area where trainees can come in and practice securing the network and other skills they need in realistic environments. And so we have training that is available. But let's talk about how we assess performance in this training. So current status for evaluating mission readiness, if you have guys who are working at an exercise, one of the primary ways that mission readiness is assessed is you've effectively got somebody coming along with a clipboard going, okay, they did this, they didn't do that. So one, it's subjective because of the check marks, and two, if you look at what's on the list, it's also pretty subjective. So that is a very subjective judgment. We've also got, and then we use multiple choice quizzes in our training. At the end of a video, it's a great way to check comprehension. Did they understand what was in the video? Do we need to re-explain something? But multiple choice quizzes, not so great for mission readiness. We have a new capability. This is brand new this fiscal year, and a lot of the credit for making this happen goes to Adam Welly, who I don't believe is here today. So this is not just recording the history file. We've actually got more than if we just recorded the history file for all the commands somebody used on the command line, because we have a date and timestamp on that. We have the prompt they were looking at when they entered that command, and of course I have removed any identifying information from what I'm showing you here today. So the question is now, we have this rich data, what do we do with it? How do we analyze it? What we would like to be able to do is we would like to be able to assess mission readiness is this trainee ready to go into the field? That's one of the biggest end goals. Additionally, optimize training schedule. When do people need to come up and re-practice on this? Is it every 6 months? Is it every 18 months? When are they ready to go on to the next skill? This would be a really useful thing for us to do. Those are kind of longer term goals. If we looked at shorter term goals, we can refine the training. Providing detailed feedback. One of the things we know from the learning sciences is that detailed feedback is where most learning occurs. When you give people feedback, they go, oh, and they change and they get better. And then refining the training modules. What do we need to explain better? How can we improve our training? So we've got a couple of long-term goals, we've got a couple of short-term goals that if we can use this information, we can start working on those goals. But getting from commands to mission readiness, it's a pretty long chain of evidence. So how do we close that gap between, okay, this is the stuff you clicked on, and this is the stuff you entered, to you're ready to go into the field? Well, this requires three things. We need to know what expert performance looks like. What do experts do for a particular task? How do they solve it? And this is not simple because experts do a lot of different things. If I were going to solve a problem and Josh were going to solve a problem, we'd probably do it differently. So that definitely makes this difficult. And then we need to make sure we're collecting the right data. Because if it's not just which commands were entered, maybe the commands are exactly the same, but the expert takes 3 minutes and the novice takes 10 minutes. If we don't have time in our data, then we're missing the big picture and we can't distinguish novices from experts. So we need to make sure we have the right data. And then we need statistical modeling because we need to be able to compare the expert performance to the novice performance. Is this trainee closer to the experts or closer to the novices? And until we have these three pieces, we can't really address those goals properly. So that's the current work right now, is building statistical models to quickly build domain models. Because we are building new training modules continuously, and for each task, we need to be able to say, well, this is how experts solve this task. So that is the current work. And when we have that, we will be able to address these short-term goals. Because when we can say, well, this is how experts solve the problem, then we can take that and say, here's the feedback, here's how your behavior could be more like an expert. And that allows us to improve training that way. So now I'm going to let Josh talk about policies and practices.
All right. Okay, home stretch. Better policies and practices. So the problem here is that vulnerability remediation can be a complex, multi-factor, multi-party process. When we think of remediating vulnerabilities, we think of something along the lines of patch management and patch deployment. However, before any of that can occur, there's an entirely separate process that must occur beforehand, and that's the vulnerability disclosure process. So we asked the question in the beginning, when the next Spectre and Meltdown happen, how do we handle this? How do we address this problem? And the answer is we develop, establish, and promote guidelines and best practices for coordinated vulnerability disclosure. This is an area of work that CERT-CC, which is a part of the SEI, has been doing for the past 3 decades. We've developed guidelines for coordinated vulnerability disclosure. We've helped co-author standards, and we work closely with the security community on various issues related to coordination and vulnerability disclosure. In addition, we provide CVD services to better help protect the nation under the sponsorship of DHS and DoD. So we're very much actively working in this area. So before we get into the part of the work, let's take a quick look at CVD and what it is and talk about why it's so complex. So CVD stands for Coordinated Vulnerability Disclosure. And what that is, it's the practice of when a vulnerability is discovered, reporting it to the vendor or a third-party coordinator, such as us, or perhaps even both, the vendor and the coordinator working together to develop fixes and mitigations for the vulnerability, and then eventually disclosing the information to the public so that users and consumers can protect themselves. So it can look like a fairly straightforward process, but once you start to get multiple parties and multiple vendors involved, such as the case of Spectre and Meltdown, it starts to become much more complicated. So just as a quick primer for those of you who may not be familiar, Spectre and Meltdown are instances of a class of vulnerabilities that arise from how modern CPU chips perform speculative execution. And they do this to help enhance the chip performance. So all modern chips do this. So it's a vulnerability that spans across multiple vendors. There's multiple vendors that are affected by this vulnerability. In the case of Spectre and Meltdown, it's much more complicated because not only do you have all the chip vendors that are affected by the vulnerability, but there's an entire supply chain of vendors, such as the operating system vendors and software and application vendors who all rely on these chips to execute their code. And so with the greater complexity introduced into the process, there's more areas where this process of coordinated vulnerability disclosure can break down. So this particular project, modeling the operations of the vulnerability ecosystem project, the goal of it was to identify factors that affect the success of this CVD process. The data that was used for this project were 11,000 cases that we ourselves had coordinated over a 24-year time span. And the information in there included things such as the vulnerability description, all the coordination emails between us and those involved in the coordination efforts, and then the dates that the vulnerability was made known to the public. Of the 11,000 cases that we coordinated, we had a public date for about 9,600 of them. And so what we're looking at now is what we did is some analysis on that data. This is just one example of some of the analysis that was performed by the research team. It's a workload analysis of the CVD data. I know it looks kind of complex, but it's actually not too bad. This is what we're looking at is a chart of the case midpoint when, for any particular case, when the halfway point was reached relative to the date the vulnerability was made public. I know that didn't sound much simpler. You look at it this way. You look at 0, anything to the left of 0 are cases that reached their halfway point prior to the vulnerability being disclosed to the public, whereas anything to the right of 0 are cases where they only reached their halfway point after the vulnerability was made known to the public. So as we can see from this chart and just taking a look, a large majority of the cases did not reach their halfway point until after the vulnerability was disclosed and made known to the public. So we can see that there's quite a bit of work that still needs to be done. A significant portion of the casework and coordination effort still needs to be done even after a vulnerability is made known to the public. In addition to this kind of workload analysis, the team developed a model to simulate the multi-party CVD process to better understand the various factors that affect the success of a coordinated vulnerability disclosure. And so what we're looking at here is a portion of the model as it pertains to early or accidental disclosure. So in the process of coordinating the vulnerability, there's an embargo period. This is an agreed upon period of time that those involved in the coordination agree not to disclose the vulnerability to the public. They're going to withhold that information from the public domain. And that's to give all the parties who are working together a reasonable amount of time to develop fixes and mitigations for the vulnerability. If there's a disclosure during that embargo period, then that's considered an early disclosure or an accidental disclosure. So if we go back to the case of Spectre and Meltdown, given the kind of the gravity of the vulnerability, the vendors that were involved in that coordination were very concerned about an accidental disclosure happening. And as a result, they limited the number of vendors that were involved in the coordination effort. So what happened was when Spectre and Meltdown were finally disclosed to the public, if we go back to this chart right here, whoops, this one, if we go back to that chart right there, there was a number of vendors that were downstream that were left in the dark that were caught off guard when the vulnerability was finally made known to the public because the vendors involved that were involved in the coordination were so concerned about an accidental disclosure occurring. So while the concern of an accidental disclosure or an early disclosure, particularly in this case, is certainly understandable, it's, at the end of the day, it's anecdotal. And it's really only one of many different factors that need to be taken into consideration in the CVD process. For example, what effect does limiting the number of vendors in the coordination have on the process? What is, perhaps by developing a model such as this, we can start to plug those inputs in there and ask those kinds of questions. What are the social costs? What's the overall cost of an early disclosure versus the social cost of limiting the number of vendors that are involved in the coordination effort? And what you may find is that, oh, well, the cost of an early disclosure actually is not that significant, whereas limiting vendor involvement, whereas limiting those vendors involved has a much higher social cost on this coordination effort. And so the goal and the aim and what this allows us to do is to take that data, plug those inputs in, and develop some findings that we can use to validate existing guidelines and establish new ones that are based on quantifiable data. So just looking ahead, from Spectre and Meltdown, CVD, this coordinated vulnerability disclosure, gained a lot of attention, and it's very clear that this is an area of ongoing work. During their testimony before the Senate, both Intel and Microsoft cited our CERT guidelines as the process they follow for CVD, and in addition to that, Art Mannion, the vulnerability analysis technical manager here at CERT, he also testified before Congress on Spectre and Meltdown. So there's a lot of interest in the area. Looking forward to FY19, what we're going to do is we're going to take the findings from this work and plug those back into updating our guidelines on CVD and put out an updated set of guidelines. In addition to that, we're going to take those, using what we've learned and feed that back into the community and the work that we do with, with the public and for DoD and DHS. And then finally, in fiscal year 19, we're gonna do some work on looking at the true risk of vulnerabilities as they pertain to the likelihood that an exploit will actually become available. And so we're working with the Common Vulnerability Scoring System Special Interest Group to see about improving CVSS to better correlate the scores with risk.
So where does that leave us? Can we read the minds of malware authors? No, we don't mind read. But we have built a fair number of tools, and as I mentioned, they are up on GitHub for providing faster analysis and better tools for the malware analyst to get into what the malware is doing and what vulnerabilities are trying to be exploited. And bringing the experience of an expert instructor to every trainee. We are building profiles of expert performance so we can show more easily the trainees how experts do things and the different ways that experts solve problems. And improving CVD practices and increasing adoption, because part of the problem is getting everybody to follow best practices. And so all three of these areas we've talked about, and they all work together to reduce risk and increase resilience. And so the PIs, we've left ample time for questions. Corey is sitting right here. He is the primary author on the malware work. I've been doing the work on the training and building the expert profiles, and I don't see where Alan is sitting, but he promised he would be here.
You promised.
He promised. So we would be happy to take questions now.
So what is being done to ensure that we are not giving our soldiers, sailors, airmen, and marine analysts a checklist to follow instead of giving them the tools to think outside the box to actually think about how that malware might have been written and what it might do?
Okay, so that's a question for Corey, I think. Do we have a handheld?
What are we doing to avoid giving a checklist and to enhance thinking outside of the box on the part of our analysts?
So our tools are static program analysis tools that require a fairly substantial amount of experience to operate. So I can't say that we've been providing checklists or making it too easy. I think we still expect that the people operating our tools are going to have a good idea of how to do reverse engineering manually by hand to begin with, and we're just making that less tedious and easier and quicker, more cost-effective, etc. Does that answer your question? I'm not fully sure I understood.
Well, I was thinking more in terms of what April's doing relative to the expert, how an expert would do it. That might be how one or two or three experts would do it.
Yeah, so what you're talking about here is actually why the problem that I described is hard, because novices tend to know like 2, 3 ineffective strategies that are kind of slow, but they'll eventually get there, whereas experts have a whole range of tools in their toolbox and different things that they can bring to bear. And so, but one of the things that makes experts so efficient is that they know when to use each tool and what each tool is good for. And so no, we don't want to provide checkboxes, but we do want to provide context for why did the expert use this tool in this scenario? Why did they do this instead of that? And so yes, what you're talking about is exactly why this problem is hard.
Something there real quick. The OO Analyzer tool that we were talking about, where the paper's being published next week, one of the things that we've done in that tool is we've taken a whole lot of very expert knowledge about how to reverse engineer object-oriented programs, and we've turned it into prologue rules, and we've codified it into a tool. So if we can teach the junior people to run that tool, they will get a lot of very expert knowledge for them in the tool, and then they just need to know that the tool's available and that it has that knowledge coded into it.
Okay, but if you're encoding knowledge into prologue rules into a tool, can't the adversaries get the tool and the prologue and know, therefore, how you'll be analyzing the malware?
Excellent question. In this particular case, we're not really talking about prologue encoding malware-specific things. We're talking about the prologue rules encoding knowledge about how the compilers work to produce executables from object-oriented code. So the bad guys don't really have any control over those aspects of the analysis unless they quit using object-oriented compilers. And the whole reason why they're using object-oriented compilers in the first place is because they're looking for all the benefits in expressivity and ease of understanding and architecture and design that they get from using those tools. So we win either way. Either we're able to reverse engineer what they're doing because they use the tools that we have the rules for, or we prevent them from leveraging those tools to have easy software development environments. Yeah, sadly, I try not to draw attention to that, but yes, that is true. There are things that we can reverse engineer better than other things, and the availability of our tool probably does leak some information about which things are more easily recovered than which other things. But that's a cat and mouse game we've been playing with malware authors for many, many years. And my personal feeling on it is that just means we have more work to do at doing better object recovery.
Well, if there's no more questions, it's clearly time for coffee.
Thank you.